It is tempting to assume that the world only operates the way we perceive it. Our frontal lobes, where our decision-making takes place, naturally lead us to count using 10 distinctive digits because we have 10 fingers. But imagine, in a hidden world, ants are capable of counting. With 6 legs, wouldn't a number system based on 6 digits make more sense to their frontal lobes? In the world of digital circuits, the limbs are not legs nor fingers. It is switches that are either on or off. So decision-making in that world works perfectly using a 2-digit system, a system that consists of zeros and ones. Let's start with some key terms. Our 10-digit system is called the decimal system. It is the system we use on a daily basis, and the 2-digit system that is used in digital circuits is called the binary system. And the number of digits any number system is based on is called the radix, or base, just like the number 6 in a hypothetical ant-invented number system. Here it is 10 in decimal and 2 in binary. But what does it mean to say that the base for the decimal system, for example, is 10, and for the binary system it is 2? It means that in the decimal system, for example, each digit in a number can count up to 10 digits starting from 0. Meanwhile, in the binary system, because the base is 2, each digit can count up to 2 digits. Note that the maximum number for each digit equals the radix minus 1. So in the decimal system, it equals 10 minus 1, which is 9. And in the binary system, it is 1 because 2 minus 1 equals 1. Let's take a closer look at how counting works. In the decimal system, we start counting 0, 1, 2, we keep going until 9, 10, 11, then all the way to 99, 100, and so on. The transition between 9 and 10 is where we need another digit to express the value of the 10. So we add 1 to the already existing 0 on the left-hand side of the 9, which is called leading 0, and adds no significance to the number until that point. And then we reset the 9 so it becomes 0. And that is because 9 is the maximum value a single digit can hold in the decimal system. Here we can see the same operation occurring again between 99 and 100. Here at 99, we reach the maximum digit, so the first 9 triggers the digit to its left, but that one is 9 too, so it triggers the next one to the left, which is the leading 0, which in turn becomes 1. And the second step is to reset all the digits to the right of the 1, so both 9s are zeroed out. Counting in the binary system and in any other number system follows the same principle. Here's how it works in the binary system. We start counting 0, 1, but then boom, we have reached the maximum digit. No problem, it is like counting from 9 to 10 in the decimal system. The 1 will trigger the leading 0, which will become 1, and then the 1 zeroes out. So we have 1, 0. Then we keep going. The 0 goes up to 1, so we have 1, 1. Then the same operation occurs again, just like in transitioning from 99 to 100 in decimal. The 1 triggers the digit to its left, and so does the latter. And then we reset all the digits to the right, so we get 1, 0, 0. Then we keep counting up the same way. 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0. Let's see an example on counting in the binary system. The example here says, count for 8 counts using the binary system. Pretty simple. Pause the video and try to solve it on your own. Alright, let's start counting. 0, 1, then we transition to 2 digits. So we add 1 and reset this one. So we get 1, 0. Then we keep going 1, 1. And as explained before, we go to 1, 0, 0, 1, 0, 1, 1, 1, 0. Now let's check if we have reached 8 counts yet. Here, 0, 1, 2, 3, 4, 5, 6. Oh, not yet. We need 2 more counts. I also ran out of space here, so let's continue up here. 1, 1, 1, and 1, 0, 0, 0. Now we have 7 and 8. And this, ladies and gentlemen, is how we count 8 counts in the binary system. To practice on your own, continue counting to 12 in the binary system. You could also check your solution online. Reflecting on the decimal and binary systems, note that to express the number 8, which is a single digit in the decimal system, we need 4 digits in the binary system. Imagine if it was a number in hundreds. Communicating those numbers in binary is convenient for circuits, yet not quite for us humans. So we have 2 other common systems we used for that purpose, which are the octal system and the hexadecimal system, or Hexa for short. The octal system is a base 8 number system with its range extending from 0 to 7, which is the radix minus 1. And the hexadecimal system is a base 16 system, so its range extends from 0 to 15. But the number 15 consists of 2 digits, so what do we do here? We'll get to that in a moment. Now let's start with the counting in the octal system first. Same principles apply here. We start with 0, 1, 2, all the way to 7, which is the maximum digit here. So it triggers the leading 0, which in turn becomes 1, and we reset the 7. So we get 1, 0, then 1, 1, all the way to 7, 7. Remember that 7 is the maximum digit here, so we get 1, 0, 0 afterwards. For the hexadecimal, we have to sort out the 2-digit problem here first. Let's see the range in this system. The range starts from 0, 1, 2, all the way to 9, then 10, but wait. 10 consists of 2 digits, which would cause major confusion in counting, but it's also under r minus 1, so it is within the range, so it must be represented using 1 digit. To sort this issue out, we replace it with the letter A, and that applies to the rest of the range as well as to any other number systems with the same challenge. So here we have 9, A representing 10, B representing 11, C representing 12, D representing 13, E representing 14, and F representing 15. And the range is from 0 to F. Now we got this obstacle out of the way, let's count in hexadecimal. 0, 1, 2, up to 9, then A, then B, all the way to F. Then and only then we have 1, 0, as F is the maximum digit in the system. Then 1, 1, 1, 2, all the way to FF. Then 1, 0, 0, 1, 0, 1, and so on. Let's see an example. Just like the previous example, count for 12 counts using the octal system. Pause the video and try to count on your own. Alright, let's start. 0, 1, 2, 3, 4, 5, 6, and up here 7, and that's the maximum digit here. So we continue 1, 0, 1, 1, 1, 2, 1, 3, 1, 4. Let's check if we have reached 12. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, we have. Now, another example, but this time it is in hexa. Count for 20 counts using the hexadecimal system. Pause the video and try to count on your own. And let's start counting. 0, 1, 2, 3, 4, 5, 6, and up here 7, 8, 9, 10. No, not 10. Here we have A, and then we continue B, C, D, and up here E, F, and then and only then we have 1, 0 or 10 here. So here we continue 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, and let's check if we have reached 20. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. Yes, we have. Let's say you saw a number in the wild, 1001 for example. In the world of digital circuits, we cannot assume that it is a decimal number. It could be binary, octal, hexa, or even a base 5 number system. So to clarify things, we use a subscript for each of those numbers. So each number must be displayed with a subscript and parentheses. The parentheses can be optional, but for this series, we are going to use them. It could be 10, 2, or other numbers depending on the radix. In the description of the video, you will find a practice PDF that includes a summary of the lesson, as well as multiple concept checking questions that cover the material in this video with their answers. Those practice questions include counting in all the number systems covered in this video. To summarize our lesson, we covered 4 common number systems we use in the digital circuits: the decimal with base 10, binary with base 2, octal with base 8, and hexadecimal with base 16. The radix or base is the number of values a single digit can hold, and the maximum value a single digit can hold equals r minus 1, or the radix minus 1. To count beyond the maximum or r minus 1 digit, first we add 1 to the more significant digit, which is the one on the left hand side. Secondly, we reset all the less significant digits, which are the digits to the right hand side. In this video, we covered counting in different systems. But is it convenient to count in binary for 356 counts to convert 356 decimal to binary? Absolutely not, as it is a very lengthy and complex process. In the next lesson, we'll learn how to convert numbers from a system to another in more convenient ways. Until next time.